Hello and welcome to some bonding. This is Andy Schweitzer, and this is our first little video on bonding. And a few things about this chapter that you're going to want to know, and maybe a few hints or insights into other videos that you might watch here, is that you can read books about bonding, entire books, and at this point this video is designed to give you just what I feel is just a bare minimum of understanding. Maybe if you were designed or you're asked, what do you absolutely need to know about this? That's it. Um, what is maybe the most important thing to know just to try and understand and start building a bigger knowledge of what this, that's all this is. So I'm going to be running through some bare minimum stuff here. Um, but with this bare minimum, you should be able to do lots of things, okay, and be successful. So in the end, the first question might be, fundamentally, why do things bond? Now, whether it's a covalent bond, which covalent, whether it's ionic, or whether it's network covalent, whether it's metallic, all of these things bond for the same reason a nice little ball rolls down a hill. Okay, as this ball rolls down the hill, it gives away energy in the form of thermal heat, whatever. It's lower energy. It is more stable. Okay. Now, the ball theoretically can roll up the hill. This would begin to call it exergonic process. It's non-spontaneous, as pull that back here, endergonic, as opposed to the other one, which is exergonic. So endergonic is as opposed to an exergonic. One process that will run on its own. This one needs to be driven pretty much constantly, or it will roll back down. So they do this in order to get more stable. Now, saying the ball can't roll up the hill, it just needs to be energy has to be driven into the process in order for endergonic process to work, and energy flows out of an exergonic process. So all of these reasons these substances run on their own is to become more stable. Sometimes you need to drive energy into them to get them to run. That just means that it is fighting the energy battle. Okay. So why do things bond? To gain a lower energy, more stable situation. All right, now on this process here, as I look at all bonding, we'll eventually look at some properties. Is why is a solid, or why is a liquid, or why is a gas a gas, and eventually come down to some properties of these things. And in that point, we have the internal factor of bonding, controlling whether something is a solid, liquid, or gas, or we have an external factor, which is things that you can do to affect whether something is solid, liquid, or gas. So whether it be raising the temperature, affecting the pressure, various things. So we're going to spend a little more time talking more about the internal factors of bonding. And this particular video is going to focus more on covalent bonding, and these are some of the things we'll look at here. What atoms covalently bond? Why do they covalently bond? And how do they covalently bond? And when they covalently bond, what are some of the consequences of covalent bonding? Okay. Now, first things first, again, bare minimum we're trying to figure out. Covalent bonding is a bond of nonmetals. So you should be able to recognize a covalent substance. If you can't recognize a covalent substance, you are sort of in deep water, okay? And that is bare minimum. So we want to make sure we have at least cover that. So in this point, if you look at the periodic table, I'll just sketch out a very rough form of the periodic table. We have our little stair step here, and over here are non-metals. So this thing is going to include only non-metals. Now hydrogen, being right here, okay, also gets lumped into this category. So common covalent compounds: carbon dioxide, carbon monoxide, water. Again, I'm using oxygen on them, but don't have to use just oxygen. Carbon tetrachloride, methane. Okay, all of these compounds contain nonmetals. You should note that organic compounds are almost exclusively covalent. So, for example, we have methane. What if we extend it out a little bit to ethane? Okay. Recognizing a covalent compound when you see one, part of that would be realizing that covalent compounds share electrons. All right. Covalent compounds share electrons. Therefore, when you see this dashes, those referring to one pair of electrons being shared. So that's a covalent compound. Again, all non-metals. You could pick out any of these guys and put them together, and you could at some point come up with something that would be covalent. Other example might be nitrogen gas, N2, O2, F2. All those form covalent compounds. So how do I recognize a covalent substance? You should be able to realize one covalent from one ionic. Okay. Next up, all right. Why do they covalent bond? Okay, well, we talked about that they are attempting to create a lower energy state, lower energy stability. Now, I'm going to add this into the next slide. Is how do they do this? Because there's not a whole lot. We already kind of talked about why they covalent bond. Okay, but we're trying to create a lower energy or more stable environment. So how do they do that? Well, we've also talked about that they share electrons. Okay. Now, it is sort of in theories and hypotheses. The main premise here is that a full outer shell is more stable. Okay, a full outer shell is more stable. Now, how you get that full outer shell to be stable is debatable, or how you get that dependent on the bond type. So we could have a situation where we have electrons that are transferred from one atom to another to fill outer shells, or they could be shared. Now, starting with just simple Lewis dot structures, we have hydrogen, which has one valence electron. Let's go with magnesium, which has two valence electrons. We can go with, let's say, boron, carbon, nitrogen, oxygen, fluorine, and chlorine. So I just grabbed a bunch of them. You should be able to indicate the number of valence electrons here. Through boron, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, and let's get rid of chlorine here. I'm going to just leave this guy. Let's replace chlorine with, let's say, neon. So 1, 2, 3, 4, 5, 6, 7, 8. Now, in this case, covalent bonds, again, are going to be only nonmetals, which would be these guys, and in this case, this over. Okay, here's two examples of some as a tweener. Could potentially, may or may not. It's a metalloid, so it does a little bit of both. Either way, we're going to fill these outer shells by sharing. Okay? For example, and you should be able to somewhat predict um, how many times an atom will bond. Okay, so just by the fact that they're sharing, we have this guy, hydrogen, only bonds one time. It can only ever bond one time. It can share one time. This guy, 4, 3, 2, 1, and this guy's full, so it's 0. Okay, so number of bonding that it can undergo. It's important to understand the fact that every time you have an unbonded pair of unbonded electron, there's opportunity for an electron to be bonded. Okay. Now, it is possible for them to go above and beyond or below. It's just different. There's always little patches to this theory, but you should be able to understand the number of times something is going to bond. Okay. All nonmetals and the number of times that it can share. Here are some examples. We have nitrogen, which is going to, and it has 1, 2, 3, 4, 5. Okay. To explain how this works, essentially, we have a very primitive way of looking at it is hydrogen has 1 valence electron. So these two guys can share here, and we draw a dash, means they can share to fill their outer shells. Now, I just drew 2 lines there, but we'd literally only have 1 line would represent 1 pair of electrons. Another hydrogen, which 1 valence electron, 1 pair of electrons, there we go. Now we have hydrogen here, a pair dot, and they share here. So in this case, they want to have a full outer shell. This is referred to as the octet rule. Now there's another version, it's called the duet rule, which is referring to the fact that hydrogen can only have 2 electrons. It's filling its 1s2 orbital. Okay, the octet rule really is referring to an atom that's filling its p6 orbital. Generally the 2p6, but you know, it could be 3p6 occasionally. So either way, and there are different rules as we get bigger and bigger. So and this is it. This is ammonia, NH3. Okay. So number of shared electrons, and we'll talk more about the bonding type in itself. But of course, water would be H2O, so oxygen, 1, 2, 3, 4, 5, 6. So it's got 2 open spots here, so it can bond with hydrogen twice. Okay, we have carbon. Let's go carbon tetrachloride. Cl, 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 and carbon middle. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And again, they're all full. These are just simple Lewis dot diagrams. Okay, and we'll get more of these later. We'll share 1 pair here. 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 These are called just single bonds. And of course, same thing works if we have carbon dioxide, where we have carbon 1, 2, 3, 4, and oxygen 1, 2, 3, 4, 5, 6, and we have oxygen here 1, 2, 3, 4, 5, 6, and these guys will share 2 pairs. One share here, 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 and I'm going to put this guy right here. Oof. And right there. So that would be another way of drawing it. Oops. 1, 2, 3, 4. 1, 2, 3, 4. All right. So again, this is just talking about how and why these atoms share electrons. If you look at it more precisely, more on a actual model level, we refer to as an orbital diagram. Now, an orbital diagram is one where it just simply shows this process happening. We could have oxygen, which is going to be 1s2, 2s2, 2p, in this case 4, which is going to be looking like this. And we have like that. We have all of our suborbitals, and we're missing a spot right here and right here. Okay. These two electrons here are referring to this electron right here and this electron right here, and we're missing a spot, as opposed to hydrogen, which is going to be 1s1, and all it has is this one electron here. So it's going to overlap the orbital electron clouds, and there is quite a lot of debate as to how this happens. The theory of hybridization is generally up in the air. You'll find that the AP College Board has dropped hybridizations from 2014 exam. But either way, we know things happen, just sometimes it's debate as to how that physically happens. Either way, so how they bond? They're overlapping orbitals to fill outer electron shells to become more stable. What are some of the consequences of covalent bonding? This is very short here, okay? But probably what I would say is maybe the number one result of a covalent bond is that of a molecule. A molecule is a unique compound, a unique setup of a compound, where we have a covalent bond here that is extremely strong and therefore holds this little package together, and it operates as a single unit we call a molecule. Okay. The result of this molecule is that we have two different types of forces. We have an intermolecular force, and we have an intramolecular force. Looks like I spelled them both inter. Inter and intra. Okay. Now, inter would be between molecules. So if we had another water molecule, let's go like this. This covalent bond would be called an intra within the molecule. Yet we get these little forces between the two, which we refer to as an intermolecular bond. Sometimes referred to as IMF, intermolecular forces. Okay. Now, in the end, anything that attracts hydrogens to oxygens, or the water molecule one to another molecule, is in the end going to be the result of what you should be aware of as Coulombic attractions. We have a force of attraction is equal to equalizing constant, charge of a positive, charge of a negative, divided by the distance squared between the two. So all of this can in some sense be explained by the Coulomb's law. So why is the hydrogen and the oxygen covalently bonding? You can say they're overlapping electron clouds in order to fulfill a full outer shell, but in reality, you dig even deeper, you could say that the hydrogen and the oxygen are essentially being attracted to each other. This guy's protons are attracted to this guy's electrons, and this guy's protons are attracted to this guy's electrons. So they're attracting to each other's protons, electrons. In the end, that is ultimately what's happening. And then, of course, what's attracting one water molecule to another water molecule is just positives and negatives. Now, one little notation you'll see around is what's called a partial charge, and it looks like this. Positive, it's got a little S-looking substance, positive, S-looking negative. So it's not a full charge, it's a partial charge, and these two attract. So in the end, if a water molecule is going to attract to another water molecule, making it a liquid or solid, we have to have some charges attracting these molecules together. And of course, if you have two charges, you have a force. If you have two forces, we have attractions or repulsions. Intermolecular forces, intermolecular attractions, that would be between two molecules attracting to one another. Intramolecular molecular force or an intramolecular attraction, again, that's the covalent bond. And that's where we'll stop today. Thank you.